already did it once in our first class. Okay? This is how things happen in real life engineering process. Not very complicated. Don't treat it to be very complicated. It's not that complicated. Are we clear about the things we need to do in implementing one class or implementing a project? Same thing. You need to figure out what to do. You need to figure out how many components you need to do the thing, and actually assign functionality to those components, and write down their algorithm as code, and test them to make sure they individually work like this, and they collectively work to deliver the requirement. We'll cover all these, but this is on higher level, this is what you need to do. Okay? That's why you guys are already capable of doing a sizable project at this moment, once you clarify what you want to do. All right? That's why we talk about, so we'll talk about team later on in the term, but basically how teamwork could happen is you can partition the work into modules and give tasks and modules to your teammates. I mean, we already talked about briefly the productivity of one engineer each week, roughly average engineer, right? You know that Facebook is not just 50 lines of code. It's a lot more than that. That's why you need a huge team of tens of thousands of people working on different components of that big project. Okay? How teamwork actually happen? Oh, well, you need to have modularity. So somebody need to partition the work into manageable sizes and give each individual teammate some work to do. Okay? Then a key thing that the architect need to control is eventually when everybody turn in their code, they can be assembled back into a real system. It could be a situation where everybody did the perfect job on the module. The whole system still couldn't work. Okay? That is the responsibility of the software architect and system integrator. They did a horrible job. Okay? So if the software architect worked it right and partition everything right and interface all my Java and functionality lined up, then integration tests just make sure they work together and they together will deliver the functionality. Okay? That's how team actually work. So to make sure team actually, to avoid situation when things that we design actually doesn't work, guess what? We have incremental development. We have daily integration or weekly integration. Okay, because all the architect knows if we let these guys go wild for a month, that thing is not going to integrate. Okay? So to make sure that what they do will integrate, actually in many development teams, you only work 6 hours on your own module. By the end of the day, the whole team actually spend an hour integrate and build a whole cohesive product out and see if it works or not. That's called daily build. And very likely, you will have weekly build. Basically, to put a check in to make sure that our team is not making architectural level mistakes. Okay? If you have say, okay, see you next year, that project is doomed. Okay? That is definitely doomed. Okay? So daily build, weekly build, 2 weeks minimum. I mean, if you don't do your integration within that time frame, yeah, you're definitely going to have integration trouble. Right? So that's how teamwork actually. So that's why a lot of teams actually can work in a distributed fashion, because they figure out a reasonable way to actually integrate different pieces together within reasonable time frame. But more and more teams are actually located together. This is a trend that's actually reversing. So when I started work here at PSU, the trend was pushing to distributed team. Actually, Intel are basically kicking people out and say, go back and work at your home. Don't come to work, right? We can cut cubicles and we can run our building to raise chickens or something like that. But yeah, we don't need you here. IBM is the one of the extreme company. Basically, everybody have a virtual office, which is their home. They don't need to come to work. But this trend has since reversed. That's why you have places like WeWork become so popular. And actually, most companies require the immediate team of you to be co-located together. Yeah, you can have teams working in different locations, but your immediate team, the people you work closely with and every day on the same code base and project, they should be together. At least they try to go that direction. So that way, actually, you can talk to each other, you can collaborate, and you can do data build, and you can discuss things and quickly fix problems like integration issues. That is a trend for team. All right. Coming back to cost-benefit analysis, it's basically determining whether a possible course of action would be profitable, right? Profit can be different things, right? So certainly a lot more time we'll quantify this by revenue and profit, right? But also there are some time when we really quantify this, for instance, when you participate in an open source project, sometimes there's no monetary return, but you actually gain fame for doing certain projects, right? But in reality is actually people make a living doing open source project, okay? All the major open source projects are actually bankrolled by major corporations, okay? It's not actually as open as you would think, okay? For instance, Linux certainly are strongly supported by Google, Facebook, Intel, AMD, IBM, and all these major corporations. Apache, I mean, the same thing. Many open source projects actually have big monetary support. Actually, people make good money doing open source projects. For instance, Intel has a big open source technology center, which they hire, thousands of engineers doing open source projects. Okay, so cost-benefit analysis is for you to determine why are you doing this. Okay, if you are not making any money, okay, then you have to ask yourself, what are you doing here? What are you getting here, right? When you come to come to PSU for a degree in computer science, you must have figured that my investment will generate return, right? I would be able to find a pretty good job after I graduate, right? Same thing, right? If you can make that calculation, you can make a similar calculation in a software engineering project and say, okay, how much time I need to develop this product, then how much this product will be sold for, or if this product is for one single organization, how much money they are going to pay me for, right? So once you get all these things figured out, then you can decide whether it's something you want to do or not. This is also called project bid, right? Many of you probably have a life experience with some other bid, right? For instance, so I don't know if you have worked with a home contractor or all kind of different contractors. They come to you and say, oh, we'll fix your washer for $50. Or another guy will say, oh, I'll fix it for $20. Then you have a good decision to make, right? Should I go with the $50 one or the $200 one, right? So what would be my decision here? Same here. If you're going to do a software engineering project, you better calculate how much engineering resources you need, right? Mainly today, I mean, your main cost are going to be your software engineer cost. Okay? Certainly, another cost you typically have to calculate is that if you use significant computing and storage resources, then you can actually now have a pretty good idea, because you can actually go on to Amazon AWS and fill in all the forms, and they will tell you how much money they expect from you every month. Right? That is why people are moving to cloud services and cloud computing, mainly because I don't want to maintain my own computer anymore. I mean, I have to maintain my own notebook for sure. I mean, laptop for sure. But I don't really want to manage a server, right? So that's why even big corporations already outsource their IT infrastructure and their servers onto Amazon.com or Google or IBM or what have you, all these cloud services, because they don't want to maintain the IT infrastructure. So that is part of your cost, but main thing are going to be your software engineer cost, right? Which we already calculated last time is actually pretty pricey. Okay, so that's major things to consider in our cost-benefit analysis. And to do that, you better be able to measure things in the process before actually things go astray, right? So actually there are many metrics. Different companies collect different things. For us, I mean, we start with most basic metrics like how many classes you need, how many lines of code, how many test cases you have to write, and those basic things. Start with those basic things. Then you can use more complex measurement tools to help you. Once you have deployed software, then there will be a lot more metrics you can measure. For instance, how many hits you have in a second, how many machines you are running at the same time, how many databases are active at the same time, how many active users, how many monthly users, how many click on certain advertisement displays, and all these things are going to be information you need to make your decision about how to modify your system, right? I mean, all the companies like Facebook and Google, they do have to provide this kind of measurement to their customer, like their advertisers, so they can see that, okay, whether my advertisement is actually effective or not, right? Same deal. I mean, basically you have to show, a lot of times this is called business intelligence, right? So you gather all this information and show that your product is actually useful. At the same time, you also have to collect information about your own product, right? How many faults you have in a month, how many outages you have in your server, right? Whether one of your servers is superly overloaded, the other server is basically sleeping, right? Whether you should do some load balancing between different servers, whether you need another database server because your response time is so bad, and all these things can be measured and can actually help you decide how you're going to change your architecture, right? How many components you have, how many serverless you want to spin up at the same time so they can serve customers, right? So those are kind of things. I mean, this actually is a significant piece, all right? So when you actually eventually, after you work for 5 years and you want to be interviewed for a senior position, a lot of questions are going to come from this direction, okay? So how you actually design certain things to meet a metric, okay? It's not just basic design question. This is when you get out of school, okay? You are asking, okay, to show that you can actually code, right? After 5 years, you become a senior, then they want you to be able to, okay, here are the target goal we have, and how you want to design your system so that your system will perform better, okay? This is called so-called system design question, okay? For instance, they will ask you, how would you design Twitter? That seems challenging, right? They are not actually want you to design Twitter, but they want you to be able to articulate what are the factors you need to consider when set up an online system like that. Okay. So you can see that the size of the product, the cost, the duration, the effort, the quality, and the fault, and these are the basic things. By no means these are the sufficient metrics. Okay, they are necessary metrics, but not sufficient. Which means that if you collect the best of those 5 metrics, you still may only see one side of your story. But if you don't have these metrics in, then you are not going to make any good decision anyway. All right? So this is computer-aided software engineering tool, basically what we talked about last time, right? What we expected from you now is a good IDE, right? You can write code, you can compile, debug, deploy fairly easily. You have a unit testing tool which you should use pretty proficiently, which is like JUnit for Java for sure. That's a very good tool. So you can apply that. That should give you so that's the tool we are talking about. And also another one is what we talked about last time. IDE testing tool. What else? Version control. Right. GitHub. Git and GitHub. So certainly there are alternatives for GitHub and Git, but Git is actually very representative right now. Okay. So for you on this level, actually, what you need are 4 things. Number 1, you should be able to have an IDE you can write your code into, compile and run. You need a testing tool like a JUnit. You need a source control tool like GitHub. The other thing you already have and already available on your computer, which is a word processor, which you can use to write documents. That's all you need on this level. Okay? Anything more fancier than this is a plus, but not necessary. You should be a fairly functional software engineer, at least you're on your level, by having all the 4 tools we talked about just now. That's your set of computer-aided software engineering tool set. IDE, testing tool, source control, and word processor, which will help you generate good documentation. Whether it's a Word from Microsoft or Google Doc, that's your choice, but that's sufficient. To be honest, at this point, you don't need anything else. That's sufficient. For my class, that's sufficient. And as you to go as an entry-level software engineer, that's also sufficient. Okay? So you don't really need many fancy tools. Make it simple. Make it simple. That's a bag of tricks in your toolbox, and you should be able to solve your level of problem questions with that set of tools. Clear? And you are going to use that in our test, in our quizzes, in our project, in our test. Pretty much that's your tool. All right, so I'm going to skip this. Version control, we're going to talk about this many times. Testing really is an important topic. The reason is, at this moment, our ability to generate a new software system is bounded by our ability to test, not bounded by our ability to code. On average, each software engineer spends 75% of their time on testing and debug, only 25% probably on writing real code. If something accounts for 75% of your daily life, you better pay attention to it, right? Because if you are not so efficient on those tasks, that can eat all your day, right? That's why testing is so much important. But first, start with this. When you write your class, always pair up with your test. You have your class, you have your JUnit class. Your own class, JUnit class. JUnit class is essentially your test harness. Okay? Go ahead.
Is the main method part of the JUnit class?
Yes. JUnit has that main, which will basically JUnit and your class will form a running program. JUnit will be responsible for main, the entry point of your program, and then essentially run the tests you want to use against your own class. Yep. So JUnit and your class basically, once they compile, become a perfect executable program. Yes, that's a very good question. You don't need to, so this is essentially set up by JUnit already. That's why JUnit, you don't have to write main. And all these, you don't, so they actually provide you a good way to write all these calls into it, right? So I strongly encourage you guys to start using JUnit actually from today, right? So this is going to be a lifesaver. It's going to save you from many possible bugs you cannot even imagine. Having sound unit level test cases is actually going to be a great performance booster for your software engineering task. Okay? All right. So this is what we're going to cover today. I'll let you guys look at the rest because most of we'll cover in the rest of the term anyway. This is just a teaser of what to come. So today we also have a programming quiz. So do you guys want to be called alphabetically to come up here, or you want to volunteer for the task? That's up to you guys. Or if you want to come here and code on the whiteboard more than one time, you're welcome. We have many more whiteboard here for you to use. I don't know if you guys have one.